With this section, we're closing out our lessons on the L'Hopital's rule. And so here we're talking about growth rates, and we're really comparing how one function grows compared to another. And so, I mean, you can probably see if we're talking about, for example, an x squared compared to an x cubed is going to grow faster than that. But what if we had something like we're comparing an x, that's what we have down here, like an x squared and an e to the x? Well, it's going to grow faster. So we can take the use L'Hopital's rule to find out if if one's growing faster than the other. So if it goes to infinity, the top's growing faster. If it goes to 0, the bottom's growing faster. So we have a couple of problems here. F of x equals x squared and g of x equals e to the x. So we can look at this and say, okay, the limit as x goes to infinity of x squared over e to the x. Now we can apply L'Hopital's rule, because right now that limit's going to be infinity over infinity. It's an indeterminate form. So that'd be the limit as x goes to infinity of 2x over derivative of e to the x is just e to the x. So again, we have an infinity over infinity situation, so we can apply L'Hopital's rule again. We have the limit as x goes to infinity of 2 over e to the x. And now if we apply that limit, we'd have 2 over infinity, which is 0. So that means that e to the x grows faster. Now, if we take and compare the natural log of x to the x squared, we would take the limit as x goes to infinity of the natural log of x over x squared. Again, if we apply the infinity, it's infinity over infinity now, so it's an indeterminate form. So we can use L'Hopital's rule. We have the limit as x goes to infinity of 1 over x over 2x. Now, if we work with this a little bit, we'd have the limit as x goes to infinity of 1 over 2x squared. And that's going to be 1 over infinity, which is 0. So this would mean that the x squared grows faster than the natural log of x. Okay. And there's one more example to look at here. Compare the growth rates of x to 100 and 2 to the x. And if you were to graph these, you'd see that x to the 100 just take off immediately like that, and the 2 to the x might be doing this. But down the road, they would, well, I don't want to give away the secret. So let's do the limit as x goes to infinity of x to 100 over 2 to the x. Now, applying L'Hopital's rule here, I think you might already see that 100. That's going to be a long process. So this is going to be a really long video of us doing each one of these. I mean, we'd have limit as x goes to infinity of 100 x to the 99 over 2 to the x times natural log of 2. Remember, that's how the derivative of an exponential works. We normally just do e to the x is e to the x because natural log of e is just 1. So then we have the limit as x goes to infinity of 100 times 99 times x to the 98 over 2 to the x times natural log of 2 times natural log of 2. And that's going to be applied L'Hopital's rule again. We have the limit as x goes to infinity of 100 times 99 times 98 x to the 97 over 2 to the x, and so we're going to have another natural log of 2, so I'll just say natural log of 2 cubed. And so I'm joking, we weren't going to do all 100 of these. We can apply L'Hopital's rule again and again until what we have is the limit as x goes to infinity of 100 times 99 times 98 times dot 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 times 2 times 1. So, and then so at that point x is just the 1. And so we've taken that derivative 100 times over 2 to the x times the natural log of 2 to the 100 power. And in that case, it would not be the indeterminate form. It would be 100, basically, this is going to be 100 factorial on top over 2 to the infinity times natural log of 2 to the 100 power. And I think it's clear to see at that point that the denominator is going to be going towards infinity and the numerator is not. Even 100 factorial is nothing compared to this infinity, so that's going to be 0. So that 2 to the x grows faster. And that's it for this overall section. Okay, next stop is Newton's method.